Welcome to this rigorous scientific lecture on modern materials discovery. Today we're going to explore how high-throughput synthesis combined with machine learning model selection is revolutionizing the way we discover new materials. Let me start by framing the fundamental challenge. Traditional materials discovery is incredibly slow and expensive. In the traditional approach, a scientist might spend weeks or months synthesizing a single material, characterizing its properties, and analyzing the results. This sequential process is fundamentally limited by human time and resources. Now consider the combinatorial problem. If you have just 10 synthesis parameters, and each parameter can take 5 different values, you're looking at 5 to the power of 10 possible combinations. That's nearly 10 million different materials to explore. 5 to the 10th power equals 9,765,625 combinations. If each experiment takes 1 week, that's 187,000 years of work. So here's the critical question. How can we possibly explore this vast chemical space efficiently? This is where high-throughput synthesis and machine learning come in. The modern approach consists of 6 integrated steps that form a closed-loop optimization cycle. Let me walk you through each step in detail. Step 1 is designing a parameter grid. This is the foundation of your entire experiment. First, you identify all the controllable synthesis parameters. These might include temperature, pressure, composition ratios, annealing time, and precursor concentrations. Here's an example parameter space for a typical materials synthesis. We have temperature ranging from 400 to 800 degrees Celsius, pressure from 1 to 10 atmospheres, composition ratios, annealing time, and precursor pH. Now, here's a key insight. Instead of a regular grid, which clusters points inefficiently, we use Latin hypercube sampling. This is a stratified sampling technique that ensures good coverage of the entire parameter space with fewer points. Latin hypercube sampling gives you n samples in d dimensions, where each parameter range is divided into n equally probable intervals, and exactly 1 sample is taken from each interval for each dimension. For example, 100 initial samples can efficiently cover a 5-dimensional space much better than a regular grid, which would require 5 to the 5th power equals 3,125 points for similar coverage. Step 2 is automating the synthesis and measurement process. This is where we gain orders of magnitude in speed. Modern robotic synthesis platforms can run 96 experiments simultaneously. These systems use liquid handling robots, automated furnaces, and parallel reactors. This diagram shows a typical 96 well plate setup. Each well represents an independent experiment running in parallel. The blue wells are currently synthesizing, while the green wells have completed synthesis and are ready for measurement. Key measurements include X-ray diffraction for crystal structure, optical spectroscopy for band gaps, electrical conductivity, and electron microscopy for morphology. All of these can be automated with modern instrumentation. The throughput gain is dramatic. What would take 2 years sequentially can now be done in 1 week. That's a factor of 96 improvement in time efficiency. Step 3 is absolutely critical, but often overlooked. Building a clean, well-documented dataset with comprehensive metadata. Here's a fundamental principle. Your machine learning model can only be as good as your data. Garbage in, garbage out is especially true in scientific machine learning. Essential metadata includes all synthesis conditions, batch information, operator identity, instrument calibration dates, and detailed measurement protocols. This metadata is just as important as the measurements themselves. A clean dataset has 3 components: input features, which are your synthesis parameters, target properties, which are your measured outcomes, and comprehensive metadata that documents everything about how the data was collected. You must implement rigorous outlier detection using statistical methods. Look for measurements that are more than 3 standard deviations from the mean, or use more sophisticated techniques like isolation forests. The z-score is calculated as the value minus the mean, divided by the standard deviation. If the absolute value of the z-score is greater than 3, flag it as a potential outlier for manual review. Step 4 is training machine learning models to predict material properties from synthesis parameters. This is where we build our surrogate model. You might ask, Why not just use physics-based simulations like density functional theory? The answer is computational cost. DFT calculations can take hours to days per material, which defeats the purpose of high throughput. Machine learning models serve as fast surrogates. Once trained, they can predict properties in milliseconds. The trade-off is that they require training data and have limited accuracy outside their training domain. For model selection, we typically compare several algorithms. Random forests are robust and handle nonlinear relationships well. Gradient boosting often gives the best accuracy. Neural networks can capture very complex patterns, but require more data. Mathematically, our model predicts the property y as a function of the input parameters x1 through xd, plus some irreducible error epsilon. We use k-fold cross-validation to assess model performance. This involves splitting the data into k subsets, training on k-1 subsets, and testing on the remaining subset. Repeat this k times with different test subsets. We evaluate models using root mean squared error, which is the square root of the average squared difference between true and predicted values. Lower RMSE indicates better predictions. Step 5 is the most sophisticated part, using model uncertainty to intelligently choose which experiments to run next. This is active learning or Bayesian optimization. The key insight is that not all experiments are equally informative. Some experiments will teach us a lot, others will be redundant. We want to maximize information gain per experiment. This creates a fundamental trade-off between exploitation and exploration. Exploitation means synthesizing materials we predict will have good properties. Exploration means investigating regions where our model is uncertain. This acquisition function landscape shows how we balance exploitation and exploration. The green region has high predicted properties, the red region has high uncertainty. The optimal next experiment is where both factors are favorable. A popular acquisition function is expected improvement. This quantifies the expected amount by which a new experiment will improve upon the current best observed value, accounting for prediction uncertainty. Expected improvement is the expected value of the maximum of 0 and the difference between the prediction at point x and the current best value x plus. We use the model's predictive distribution to compute this expectation. To estimate uncertainty, we can use ensemble methods where we train multiple models and measure their disagreement, or Bayesian approaches like Gaussian processes that provide uncertainty estimates naturally. Step 6 is validation. We synthesize the materials that our model predicts will have the best properties, but critically, these must be materials that were not in our training set. This is the ultimate test of whether our model has learned meaningful physics or just memorized the training data. If the model generalizes well, the predicted best materials should indeed have excellent properties when synthesized. A practical success metric is, if we synthesize the top 10 predicted materials, how many of them actually have properties in the top 10% of all materials? This hit rate tells us if the model is truly useful. This bar chart shows validation results. Our model predicted 10 materials as top candidates. When synthesized, 8 of them were actually in the top 10%. Random selection would give maybe one hit. This demonstrates the model learned real structure-property relationships. Let me walk through a concrete example of this entire workflow applied to discovering new photovoltaic materials for solar cells. The goal is to find materials with an optimal band gap for solar energy conversion between 1.1 and 1.5 electron volts with high stability and low cost. For step 1, we design a parameter grid for metal halide perovskite synthesis. Parameters include the A-site cation, B-site metal, halide composition, and processing conditions. The parameter space includes choices for the A-site cation, B-site metal, and X halide, plus processing conditions. With compositional mixing, we have over 10,000 possible combinations to explore. For step 2, we use a 96-well microplate synthesis platform with automated optical absorption spectroscopy to measure band gaps. Each synthesis takes 2 hours, measurements take 10 minutes. The throughput is 96 wells times 24 hours divided by 2 hours per synthesis equals 1,152 materials per day. That's incredible, compared to traditional methods. For step 3, we build a dataset where each entry includes the synthesis parameters, the full absorption spectrum, the extracted band gap, and stability metrics like time to degradation. For step 4, we start with 500 initial samples from Latin hypercube sampling and train a gradient-boosting regression model to predict band gap from composition and processing parameters. Our initial model achieves a root mean squared error of 0.15 electron volts on cross-validation. This is pretty good considering band gaps range from 1 to 3 electron volts in our space. For step 5, we use expected improvement to select the next 100 experiments. The acquisition function identifies compositions with high predicted performance and high model uncertainty. For step 6, we synthesize the top 10 predicted materials at larger scale to make actual solar cell devices and measure their power conversion efficiency under standard test conditions. The results are impressive. We screened 800 materials in 3 weeks. The best material found was cesium 0.1, formamidinium 0.9, lead iodide 2.7, bromide 0.3, with a band gap of 1.48 electron volts and efficiency of 19.2%. Traditional approaches would have taken 3 years. Let's do a quick back-of-the-envelope calculation to understand the cost-benefit of this approach. Traditional approach: one graduate student working for 3 years at $50,000 per year salary, plus $20,000 per year in materials and equipment. Total cost, $190,000. 3 years times $70,000 per year equals $210,000 total investment. High-throughput approach. Robotic platform costs $200,000 as capital equipment, but it's reusable. Running cost for 3 weeks is about $15,000 in materials and student time. If we amortize the $200,000 platform over 10 projects, that's $20,000 per project, plus $15,000 running costs equals $35,000 per project. We achieve a 52 times speed up, and the cost per material discovered drops by a factor of 6. Plus, we explore the space more thoroughly, increasing the chances of finding the truly optimal material. Now let me address an important question. What are the limitations of this approach? It's not a magic bullet. Limitation 1. The approach is bounded by the parameter space you initially define. If the best material uses a chemistry you didn't include in your grid, you won't discover it. You need chemical intuition to set up the search space. Limitation 2. Some properties are difficult or impossible to measure in high throughput. Mechanical properties, long-term stability, and device-level performance often require large-scale samples and extended testing. Limitation 3. Model accuracy is fundamentally limited by training data quality. If your measurements have high noise or systematic errors, the model will learn those errors. Rigorous experimental controls are essential. Limitation 4. There's a significant upfront investment required in automation infrastructure and data systems. This makes sense for large research programs, but may not be practical for small exploratory projects. Let me briefly touch on a more advanced topic: multi-objective optimization. Real materials discovery usually involves optimizing multiple conflicting properties simultaneously. For example, in photovoltaics, you want to simultaneously optimize band gap for efficiency, stability for device lifetime, and minimize material cost. These objectives often conflict. High-performance materials may be less stable or more expensive. The Pareto front shows a set of non-dominated solutions. Green dots represent materials where you cannot improve one property without sacrificing another. These are the optimal trade-offs. Mathematically, we're maximizing multiple objective functions f1 through fm simultaneously. We use multi-objective Bayesian optimization or genetic algorithms to explore the Pareto front efficiently. Another advanced direction is integrating machine learning with physics-based models. This combines the speed of ML with the interpretability and transferability of physics. A hybrid approach uses density functional theory to calculate properties for a carefully selected subset of materials, then uses machine learning to interpolate between these high-accuracy anchor points. This reduces the number of expensive DFT calculations needed. Using physics-informed features like electronic structure descriptors, bond lengths, and coordination environments as inputs to ML models significantly improves their generalization to new chemistries compared to raw composition features. Let me share some real-world success stories to illustrate the impact of this approach. Citrine Informatics used this workflow to discover new high-strength aluminum alloys 10 times faster than traditional metallurgy approaches. Their ML-guided search found alloys that exceeded the performance of materials that took decades to develop. Researchers at MIT used high-throughput screening with ML to discover new solid electrolytes for batteries. What would traditionally take 5 years of sequential experiments was accomplished in 2 months. Lawrence Berkeley National Lab applied this approach to discover metal-organic frameworks for carbon dioxide capture. Their models predicted CO2 uptake capacity with 95% accuracy, leading to discovery of record-performing materials. Let me give you some practical tips if you want to implement this workflow in your own research. Tip 1. Start small. Don't immediately try to screen thousands of materials. Begin with 50 to 100 samples to debug your synthesis protocol, validate your measurement pipeline, and train initial models. Tip 2. Invest heavily in data infrastructure from day one. Use laboratory information management systems, enforce metadata standards, and implement automated data logging. Poor data management will cripple your entire effort. Tip 3. Start with simple interpretable models like linear regression or random forests before moving to complex neural networks. Simple models are easier to debug and often work surprisingly well. Tip 4. Never trust your model blindly. Always close the loop by experimentally validating predictions. Models can fail in unexpected ways, and experimental validation is the ultimate ground truth. Tip 5. This work requires deep collaboration between domain experts who understand the materials science and machine learning experts who understand the algorithms. Neither alone is sufficient. Looking to the future, we're moving toward fully autonomous materials discovery laboratories, where the entire workflow, from design to synthesis to measurement to model update, happens without human intervention. These closed-loop systems can run 24 hours a day, 7 days a week. The ML model continuously updates as new data arrives, and the system autonomously decides which experiments to run next to maximize learning. This diagram shows the architecture of an autonomous lab. The robot synthesizes samples, automated instruments measure properties, data flows to the ML model which updates predictions, and an active learning algorithm selects the next experiments to maximize information gain. The cycle repeats continuously. Early prototypes of self-driving labs have demonstrated discovery speeds 100 times faster than human-guided research. The University of Toronto's self-driving lab for organic chemistry discovered new reactions in days that would have taken years. However, challenges remain. These systems must be extremely robust to equipment failures, they need to handle edge cases gracefully, and they require sophisticated error detection and recovery mechanisms. Let me summarize the 6-step workflow we've covered today. Step 1. Design your parameter grid using Latin hypercube sampling or other space-filling methods to efficiently cover the search space. Step 2. Automate your synthesis and measurement pipeline to achieve high throughput, aiming for at least 10 to 100 times speed-up over manual methods. Step 3. Invest in building a clean, well-documented dataset with comprehensive metadata. Data quality is absolutely critical. Step 4. Train machine learning models to predict material properties, using rigorous cross-validation to assess performance and prevent overfitting. Step 5. Use model uncertainty and acquisition functions to intelligently select the most informative experiments to run next, balancing exploitation and exploration. Step 6. Validate your model by synthesizing the predicted best materials that were not in your training set and measure their actual performance. Here are the key takeaways from this lecture. High-throughput synthesis, combined with machine learning, enables 10 to 100 times faster materials discovery compared to traditional methods. This approach is fundamentally data-driven, but it still requires deep domain expertise to set up the search space, design experiments, and interpret results. Active learning strategies like Bayesian optimization maximize the information gained per experiment by intelligently choosing where to sample next based on model uncertainty. Experimental validation remains essential. Models are tools to guide discovery, not replacements for actual synthesis and testing. The field is moving toward autonomous closed-loop discovery systems that can operate continuously without human intervention, further accelerating the pace of materials innovation. This integrated approach of high-throughput experimentation and machine learning is fundamentally transforming how we discover new materials, making it possible to tackle previously intractable problems in energy, medicine, and sustainability.